room. And so we'll get started in just a second. All right, people online, can you hear me?
Yes.
Great. I'm going to share my screen. Can you see my Google slide deck? All right, great. Thank you, Peter. Okay.
And, hold on, I'll be typing questions from in the room, questions and answers into the Slack, because in the previous breakouts, it's been hard for people online to hear the questions in the room, and sometimes vice versa. So make sure you join the breakout _AO in post-HST era Slack channel.
Okay. All right, so let's get started. So part of the motivation, I mentioned this in the other room as an intro behind this, is thinking about the near term and far term planning. We've heard from the AO Future Studies group about planning processes happening around the AO side of things, but we're here today to think about the back-end instrumentation side of things, and mostly focusing on what science we might be interested in. So let's, for now, try to stay agnostic about what instruments might be on the table, but just think about your science requirements. So to get us thinking about that, we're going to have some representatives from the HACA team just give us a quick reminder as to what's coming with HACA. We're going to have people talk to us about ORCAS. We have the ORCAS PI here. And then Jessica's going to talk a little bit about potential future MC-AO LGS upgrades that might also get us there. And then we're going to move into talking about science. Sam, are you here? Yeah. Oh, actually, yeah. Before we get into the HACA stuff, I wanted to mention over kind of the next year, I'm going to be working on an effort to do some planning about visible light backend instrumentation. And so the kind of kickoff for that is today's breakout session. In the fall, I'm going to be encouraging you all to, if you're interested, to join a diffraction limited visible light science working group. And one of the main tasks for that working group will be putting together a 2-day online workshop in February and March. I'm thinking probably one day we'll be talking about science, and the second day could be talking about instruments based on the science that we talk about on the first day. And so if you're interested in making sure that you have your science as input and you want to make sure this goes in the direction you're interested in, please join this Visible Light Science Working Group. And so I will tell you about how to do that in just a second, express your interest. And then we've talked about having a conceptual design for a first generation imager sometime in 2020. And this could be something that HACA could use and might also be relevant for ORCAS and other considerations. So the idea of all of this effort is really to be complementary to the AO-FSG planning effort and the broader Keck strategic planning effort, but thinking again about the back-end instrumentation side of things. Before we get into HACA, ORCAS, and other stuff, does anyone have any questions? Okay, Sam, are you ready to get started?
Sure. Thanks, Mike.
All right, just let me know when to change slides.
Sure. Yeah, HACA would improve the performance, sky coverage, and science reach of Keck 2AO. So the project consists of 2 parts. The first one is upgrading our existing deformable mirror with a higher order DM. So it would have an activator pitch of about 2.5 millimeter down from the current one of 7 millimeter. So in terms of number of actuators, we'll be going up from 349 to over 3,000 actuators. The expected performance improvement in terms of wavefront aberration reduction, mainly from fitting and aliasing errors, is about 130 nanometers. As you can see on the estimated strand plot on the right, with respect to the current one, that is the solid red line, and we expect to have improvement for very bright targets, the dashed line. In addition, having a finer pitch size would enable us to improve some of the other error terms, basically mostly static operations, semi-static, and maybe even dynamic aberrations, reduction through enabling finer compensation. That's what's shown with the dotted line on the plot. As you can see, such improvement is necessary if you want to go to the shorter wavelength. And the second one upgrade is implementing a truth sensor in the near infrared. This is to use the existing pyramid wavefront sensor, but going to a coarse setup that is going down to say 5x5 subapertures also, and use that as a low order wavefront sensor corrections for LGS case. Okay. And next slide, Max. This is the expected performance improvements for the LGS case. Okay, yeah, next one, Max. Yeah, now specific to the exoplanets case, we expect this upgrade would enable exoplanet science, not only in imaging and spectroscopy, down the road for photometry as well. The impacts are increased control radius from 350 milli arc seconds to about 1 arc seconds, and improved limiting contrast. We expect direction sensitivity to go up by a factor of 10, and gain in efficiency by a factor of 4 for spectroscopic follow-up studies. And more importantly, this would also enable visible wavelength science. To be clear, yeah, we need to not only upgrade the mirror, we need to work on reducing some of the instrumental aberrations here. If you're able to do that in wideband, in theory, we could reach as much as 40% strand, and a lower one for other wavelengths. Okay. And the configuration will also enable us to look at some of the faint exoplanet science cases, such as protoplanetary cases and debris disk science, to operating in the LGS mode. Okay. The next one. Thanks. Yeah, for non-exoplanet science case, we will have some new operational modes that would involve not having the need to have a visible sensor at all. That we'll be able to, since we'll have a truth sensor in the near infrared for targets of say about a H magnitude of brighter than, yeah, it should be brighter than 15. In the LGS case, we should be able to operate without the need for low bandwidth wavefront sensor in the visible wavelength. Similarly, for NGS case, a magnitude of what H of 12, we won't require any visible guide stars. And since the upgrade is planned on Keck 2, we will be able to do complementary imaging observations for kappa science and possible prototype for visible imager science, and the upgrade would also enhance IFS capability for future instruments such as scales. I think that's it, Max.
Okay, I don't want to go into too many questions, but any quick questions for Sam about Haka while we're here? And Anybody online, feel free to put your hand up. All right, we have one from Dimitri.
What is the limiting term in your project?
NGS or LGS?
NGS.
So the question was, what is the limiting error term in your error budget for visible light NGS science?
What we assumed for, okay, let me, can you go back to the slide, 2 slides up? Okay. That's right. On the top right one, the NGS plus HACA DM, that accounts for only the improvements due to reduction in fitting and aliasing error. Okay. For the other error terms, we assume that we will have a better understanding of instrument operations. That is, as I mentioned, static and semi-static operations, and we hope to address some of the operations in the science instrument as well. So the curve, the projector on the top assumes that we will have some advanced wavefront sensing techniques in place to make use of the higher order DM.
All right. Any questions online? All right, then. Okay, sorry, go ahead, Claire.
I have a question. Can you go back a couple slides? I think it's a couple slides. The one where you say the improvement in I band, R band.
I think that is the one.
Yeah, that one. Strail ratio improvement. So I didn't understand what that meant. Because it seemed like the improvement was, as a percentage, much higher than that in the graphs that you were just showing. Show me, just let's take I band, 18% Strail improvement, and then go back to that graph and show me where that came from.
I think it was incorrect. It's not an improvement. It is the visible strail ratio.
Yeah, that's right. I mean, it's an improvement of almost a factor of 2 based on this. If you compare the solid red curve and the dashed red curve.
Sure.
Maybe he means he's adding another 20%.
Anyway, it would be interesting. It's more dramatic, and I'm thinking in terms of your next proposal to NSF. It's more dramatic to say the Strail ratio at 700 nanometers or 900, whatever it is, improves by a factor of blah, blah, blah.
Okay.
Because it's obviously way more than 10% or 11% or whatever was on that thing.
It is, what I presented is strail ratio. It's not strail ratio improvement. Okay.
Yes.
In terms of improvement, I agree with you. It's much more than improvements.
All right, we have one more question from Carl. Let's go ahead, Carl, and then we'll move on to the next.
Yeah, I seem to remember that Palomar had a wavefront sensor like this. Is it called PAL 3K or something? What was the experience there in doing these high order corrections? Is that lessons learned we can look at?
So Carl, I can address that, but it's a big topic. Is there a particular aspect of?
Just general comment that should be looked at.
Right. So like we went to 10 times the number of actuators, and we rolled out POEM 3000. We saw about 15 to 20% gain in K-band strail. It went from 65 to 85%. on bright stars. We never quite achieved the error budget that we wrote down, which was, I think, a total of 120 nanometers RMS on bright stars. We kind of bottomed out at 150, and we're not quite sure what floor we hit. So that might be a snapshot, but there's a lot of detail that we can discuss.
All right, and I'm going to recommend we take that detail to Slack so that we can move on. Thank you again, Sam, for talking to us about Haka. Elliot, are you there to start talking about ORCAS?
Sure, can you hear me?
Yes. Thank
Okay.
you.
Well, hello, everyone. Happy to be here today. Thank you for your time. Today, we're going to talk, well, at least I'm going to talk about the ORCAS-Keck Prime Mission Proposal, but I just want to make you aware of some other activities we have. To begin with, we have a spacecraft technology demo that was funded on our side. So you will see a spacecraft fly with an ORCAS laser sooner than you thought. We have an investment together with Keck in delivering a visible instrument prototype that we've started working on together with Max, Rebecca, Peter Wizinovich, and some others at Keck. We have the next step for ORCAS, if ORCAS succeed, already being in formulation mode. So that's the ORCAS constellation for larger field of view and sky coverage. This is kind of the future of ORCAS moving into a constellation. And we have formed science teams that cover multiple scientific topics that touch both near diffraction limited visible science as well as near infrared. And many of you have been in some of those things. In short, I just want to focus for a second what ORCAS provides. ORCAS actually carries two payloads, which we don't talk a lot about. One of them is the flux calibrator. It's like they're not going to be the focus of our topic today. And the second one is a laser beacon that's supposed to act as an ideal NGS.
Oh yeah, you just cut out.
Oops, can you hear me now?
Yeah.
Okay, so carry two payloads. One of them is the flux calibrator. The second one is a laser payload, which acts as an ideal NGS when and where you want it or need it, among other things. So let me just, if we can jump to the next page. Thank you. So in short, we have an entire 150-page report that dive into the details of every single item that you see here. I intend to release it to all of you at the end of this conversation. I'm going to send the document to Max so all of you can review it. But let me kind of take you through the big picture. On the right, you see the 5 major systems that come together to form the Keck ORCAS mission proposal. That's the spacecraft, the flux calibrator, the payload, and the Keck Observatory. I should say 4 and not 5, sorry. You can see the main characteristics of our mission, and in a second I'll dive into the details. It's a community-driven observation program formalized by our science teams and partners, both at Keck and in other places. I won't go too much into the technical details because I'll talk about them in a second, but we aim for a 2026 launch with a 3 years mission prime time. And the budget of the mission is estimated at $75 million. I'll give some more details about that. But I think most important is it's an investment, not just in ORCAS-Keck mission, but also in Keck itself. Even if ORCAS mission is not successful, the investments that would be offered to improve Keck would prove well worthy, including the development of new instruments and upgrading of the AO system, and all of that through a funding pipe that, as of today, doesn't really exist other than NSF, which the amounts there are much smaller. So typically, I'm being asked how much funding is being available for Keck. I'll talk more about that in a second in the program. Can you jump to the next page, please? I just want to talk very widely about the science that ORCAS-Keck mission proposal covers. Our leading science cases include active galactic nuclei, the high redshift universe, flux calibration, dark energy with supernovae, excuse my typo there, and exoplanets. Each one of those science cases is spread upon our report upon multiple pages, anywhere from describing the questions we're trying to answer down to a detailed science traceability matrix that describes the The specific requirements in order to conduct those observations, I think one of the most interesting science cases for a near diffraction limited visible science is active galactic nuclei. The image that you see on the top is just one example of how a target would look like with the different separations we are showing here. And basically, I think the message of this image is there is an entire range where we cannot separate by imaging pairs of active galactic nuclei. And that regime could be open to us if we kind of push towards that angular resolution. At the bottom, you see the effects of the flux calibrator instruments on different science cases. And again, I have 5 minutes, and this is 1 minute out of the 5. So please, if you're serious and you want to learn more or have more questions, read our report. It's a long and very detailed report. We try to put a lot of energy into it, and we actually did. Next page, please, Max. This is a figure that in my mind should tell all the story to everyone. If you have any issues with the numbers or the values that appear here, if you want to talk about angular resolution predictions, you can talk more with Peter Ruzinovich. If you want to talk more about sensitivity calculations, you can talk to Carl. He's also here and help us kind of go through this. In short, if you look to the left, you see the predicted angular resolution, where the bottom is the optimistic scenario and the top is the pessimistic, or what we call median conditions scenario, and the cost of each one of those missions to NASA. So without talking too much about this, you see that when it comes to angular resolution, kind of clubber everyone with the head, and on the price, we're talking about factors between 100 and 1,000. So this is a reason, and actually we have, as civil servants, fiscal responsibility. If this thing even has a chance to be right, in this kind of price level, it should be further explored and developed, and we are moving in that direction. As you noticed earlier, it's not just a mission proposal. We, and me specifically, invest money in staff, in instruments at Keck, in young scientists across Keck campuses, hopefully soon, and we try to advance our understanding of the system as much as we can. On the right, you can see our sensitivity calculations. Just to give you some reference, for example, Mavis sensitivity calculations declare a 25 magnitude 5 sigma in 1 hour, not us, Mavis. But what you see here is our prediction for a 10 sigma at 10 kilosecond exposure, just so we can calibrate it with other observatories, and it becomes very clear what happens in the visible, and that's because of how the background drops at those wavelengths. That's the main driver for that reduction. And if you want to talk more details about that, we can, or any of those things. I think the most important thing to take from this figure is that we are really, by combining a space asset and Keck Observatory, enable unprecedented, in at least the near term, angular resolution and sensitivity that would be enabled at low cost and could be deployed quite fast. Can we jump to the next slide? And how am I on time, Max? Am I too late?
Go fast.
Okay, I'll go fast. This is just the landscape. You should all know this. Upcoming Webb, Roman. You can see the timing for ORCAS, upcoming ELT from the European side. Future of GMT and TMT, we're waiting to learn about. So is Habax and Louvois. And you can just see how ORCAS is very well positioned with respect to the timeline. Can we jump to the next one? You can see the cost in compared to other space investments or future investments in ground observatories. If this figure doesn't tell you what you need to know about cost, I'm not sure what else I can say. The savings are meaningful if this could be done. And let's just jump to the last page. So many people ask us, is this a MIDEX? Is this a SMEX? Is this a whatever? So let's just start one by one. So number 3, the spacecraft bust is signed by BCT CEO. This is the cost for the spacecraft. It's a TRL-9. It's on shelf. It was launched this June, or another model of it was launched, exact same model. So we know what the cost is. The payload laser source has been signed by the 2 different competing companies, CEOs. So that cost is down. Operation cost is overestimated, in my opinion. You can see the contingency at 30% and 15%. You can see the investment at Keck ground adaptive optics system and at the Keck visible science instrument here. We're talking about an investment of around $20 million just in hardware, basically. And development plan, this entire budget was a grassroots estimate performed by Keck itself. So Peter Wizinowicz led this cost analysis. We are going to go through another rigorous one as we submit our mission proposal, hopefully this December. Or being selected for a direct admission, that's another option that came up 2 weeks ago. And that will depend on decisions at the SMD and the APD level. And I'll stop here. I hope I didn't talk too fast or too much.
All right, thanks a lot, Eliad. We're going to take a few minutes for questions because I think there might be some about ORCAS, and then we're going to direct the rest of the questions to Slack. So we did in the room first last time. So is there anyone online who has a question for Eliad about ORCAS? All right, Claire, go ahead.
Elliot, I forgot what the flux calibrator is going to be used for. Can you remind us?
Yeah, sure. So we actually have 2 science cases that are supported by the flux calibrator. I don't think I can share my screen here since we are presenting this. If you can jump up in my presentation to the science cases, really useful, thank you. So we have 2 science cases that are supported by the flux calibration. One of them is dark energy with supernova, so better constraining the cosmology measurement of dark energy. That would be the first one. If you go to our report that I will send over, that would be section 2.2. I'm trying to kind of be short here. And the second one is flux calibration, where the science objective are to provide SI traceable flux calibration to ground-based telescope to dramatically reduce systematic errors in the measurement of dark energy and to characterize the stars hosting exoplanets. That's Peter Plavchin can talk more about that. I'm not sure if he's here. I'm not sure if it was too high level, Claire.
Oh, that's good. Thank you. I had forgotten.
Yeah. So flux calibration and exploring dark energy with supernovae are the 2 main science cases here.
So Eliad, you don't need to send me the report. You can just post it directly in the Slack channel.
Oh, great. I'll do that. There you go. I'll do it right now even.
Cool. All right. And then we have one more question online from Ben.
I was just wondering about the achievable tip tilt, residual tip tilt. Like, is it possible to align this behind a coronagraph at, the few milliarc second tip tilt level? Or if not, are there future plans to do that?
Yeah, so Peter, can you hear us, Wizinowicz?
Yeah, Elliot.
Maybe you can try to take that one.
Yeah, so we've understood from the spacecraft position information that we should know it, correct me if I'm wrong, Elliot, at the 5 milliarc second level or something like that.
Yeah, we could actually take it down to guarantee 3. It's 3 sigma confidence.
Right, and then we'll know the, so that gives us sort of an absolute position, and then we know the trajectory of that spacecraft for some period of time. And so we'll be offsetting, basically controlling the offsetting of the AO wavefront sensor with respect to the science instrument to keep it fixed at something like the 1 or 2 milliarc second level.
Thanks.
Hi, sorry, we got kicked out. Ben, did you have your question answered there? Great. Okay. All right. Are there any questions in the room about ORCAS? All right, cool. All right, Dimitri. All right, so Eliad, the question was, can you remind us about the observational constraints, such as how many hours or how long we can look at a given target, how many targets per mission?
Yeah, so can you roll back to slide number 2, I think, in my...
Is this
Yeah, so you can see it here. We're talking about, at least at the first mission, before we talk constellation, 300 different AO observations with windows of period of observations that go anywhere between half an hour to 3 hours, depends on the target declination. We have an entire chapter in the report that addresses that. That's a quick answer. The longer answer is you need to tell me what your target is. And we actually built an entire optimization algorithm that would optimize an entire science program and give dates and times and location based on the mission planning to enable a more fruit-bearing program. So I hope this was a good enough answer, Dimitri, or do you want me to expand?
That was a good answer. Thank you. And other people with similar questions can move to Slack. So we're going to move on to the last part where Jessica is going to talk for a second.
Okay, so both HACA and ORCAS are aimed at getting us into optical AO. However, they both have to contend with the fact that the corrected field of view will be small, very small, a few arc seconds in the optical. So I was interested in starting to think about what it would take to get into optical AO, not just for natural guide star, but for laser guide star, and also with a bigger corrected field of view. In the post-HST era, we will not have high-resolution optical capability in space, or at least not one that's very multi-purpose. Roman, for instance, will have a V-band filter, but it's in survey mode. So what is the power, really, are you going to be done with your HST style science after HST is done? Or would you like to continue? So we've seen Elliot highlighted and Sam as well, the power of getting diffraction limited science at short wavelengths with such a large telescope. We can resolve stars and binaries in high density systems, conduct really high precision astrometry, resolve supermassive black hole spheres of influences for very low mass black holes, all kinds of crazy things. So we're really very interested in your science cases up in this regime. What does this wide field diffraction limited AO give you? We're talking about fields of maybe 30 arc seconds to 1 arc minute, maybe, with a fairly uniform point spread function over that field. And we're certainly not the only ones thinking about this. There is a reasonably mature and semi-funded project called MAVIS, which I think you heard earlier, that is already aiming to do this on the VLT. And it's pretty astounding. You can go read their science book. It's pretty impressive. And I think we'd all be interested in very similar science. What they're aiming for, again, is what you see on the left here. Sort of high angular resolution, and this cut off, this is sensitivity of some kind over here, up all the way into B and V band. So we're not just talking about red optical, but pushing into the blue. And again, over a 30 arc second field of view. So I think that's all I had to say. It's just really at this point, science. What is the science case to drive it? It won't be easy. But there's no technical showstoppers, I think. All the technologies exist for us to do this. It's just a matter of cost. And it certainly is in line with an ORCAS constellation future as well. So be thinking about that. I think we're going to launch into science discussion.
Yeah. Okay, so for the rest of today, we had this idea to put everyone to work. It's, after 5 on a Friday, you're all tired of listening to other people talk. And so we've prepared a questionnaire that's similar to a bunch of the other questionnaires you've seen for some of the other instruments. But it's really right now about science. It's maybe a bit more open than some of the other instrument questionnaires right now, because it's just about science. What visible light capabilities are you interested in? So there's a QR code here. I'm going to put this form link into the Slack chat for everyone online. For everyone here in person, what I'm going to recommend is that we get into groups of at least 2, maybe 3, and kind of talk through these science cases together. I'm going to encourage more senior people to try to go with more junior people who are less familiar with some of the things we might be talking about. So,
Max?
Yes.
The QR code says, I need permission. This form can only be viewed by users in the owner's organization.
Oh, that's annoying. Give me 1 second. I thought I fixed that, but clearly not.
You could also paste the address there into the chat, maybe.
Yeah, I'll
I
do,
pasted it into Slack.
okay, oh, yeah,
but
and
maybe it didn't-
I'll do it in the chat as well. Okay, it's in the chat, and let me try and figure out what's going on with this permissions.
Yeah, the link in the Slack says the same thing.
Okay, anyone? All right, I should, it says anyone on the internet with this link can edit. Okay, I'll give you.
It's that one.
Yeah. Well, it might give them the like editing version, not the filling out. Give me one sec. This is kind of obnoxious. I don't see where that permission is. Yeah. So I can share the editing version to anyone, but
Oh, here, I found it. It's under settings.
okay.
Okay, try now.
Try now. Success. Okay,
I
great.
did it. Great.
All right, cool. So let's do that. We have until 5:35 here before we need to be back in the other room. So let's get started. If we could have Sam and Eliad maybe keep an eye on the Slack and Zoom channels to answer any questions people have about those systems that might help. That would be much appreciated. Sure.
Think big.
Yeah, think this is not necessarily a Hakka science case, not even necessarily ORCAS, just, you know, what's the science you want to do in visible light? Yeah, as Dimitri says, go small. Dim your expectations.
Anyone want to? How many do you want us to work with? Groups of how many?
Let's do groups of 2.
Yeah.
Senior people, you find junior people. Don't make them come to you.
How do we do this?
Yeah, it's harder to work in groups for those of you online. So maybe those of you online, you're by yourselves.
I love the way the polarimetry question is being served.
Oh, everyone, the last thing I'm going to mention is that if you're interested in joining this visible light instrumentation group that I mentioned, there's a question on the form where after you put your name in, your email address, there's a yes or no if you're interested in working with that group. So those of you, even if you're not doing any science cases right now, you could think about at least filling out that part. All right, everyone, just a reminder, we got 5 minutes left, so start getting your answers into the form. All right, everyone, I'm gonna shut things down because we're supposed to go back over to the other room. Is there anything that anyone online wanted to add, or any final thoughts from anyone online? All right, Claire, go ahead.
I think we at least need to consider the importance of having an IFU, not just taking pretty pictures.
Yes, definitely. Yeah, and I think I put that in on the form too, so it should be an option for people who are interested there. And I think there's lots of interest from the ORCAS team in having an IFU, and I'm sure there are a plethora of science cases where that could benefit. Great. All right. Any other final thoughts from anyone in the room? Okay, well, thank you everyone for starting to think about this. As I said, this is kind of the start of a year-long planning process, so hopefully we'll have lots more of these discussions soon. Take care, everyone.
Thanks, Max.
Bye.
Thank you, Max. Good job.